Excuse me. Oh, where'd my water go? Ah, there it is. Sorry. Let me take a quick sip of water before I begin. Okay, there we go. So for at least our stuff due this week, we have chapter 4 is due midnight today. And then chapter 5 will be due on Friday, September 18th, okay? So we've gone completely through chapters 3, 4, and 5. All the videos of those are posted online, and all the class videos are also posted online with our goals. So remember, our class videos only have the top 3 goals, the top 3 things we're focusing on. The main videos have all the other details associated with it. So, you know, a good way to study is to, you know, watch the main video, write down questions, then come to class and then look at those 3 main things that I wanted to focus on. Those tend to be the tougher things. And then ask questions, and then we can also get additional information about the class and stuff. And so, but don't forget that those other videos online. I will be posting chapter 7 videos today, and then I'll have chapters 8, 9, 10, 11 posted over the weekend, because that will be all the videos required for our next exam, which is in next month, but don't worry about that.
I have a question.
Yes.
Are you going to change the homework date for chapter 7 on Top Hat? Because it says it's due the 18th, but you're saying chapter 5 is due.
Yeah, I should have changed that already. Chapter 5, chapter 7 should not be due on the 18th. Let me go ahead and modify that. It will not be due until, let me look at our class schedule here. So I'm going to be going through chapter 7 today. So yeah, I'll have it due on the 21st. That's Monday, the 21st.
Okay, thank you.
So thank you for reminding me of that. Details, edit, 21st, save. There we go. Thank you very much for reminding me of that. Okay, and then chapter 6, which is chirality. Next week, we'll do all of chapter 6, and the second half, we have a group activity, which is helping apply all of our chirality rules to naming things, and then also how to draw them in 3D. So that's what our group activity will be next Wednesday. So, and then again, what you'll do is you'll complete that task, take a picture and upload it to Canvas. So, but we don't have to worry about that till next week. So we're going to finish up chapter 7 today. And the reason I split those up is that we started a little bit about mechanisms and what they are. And I want to jump on chapter 7 because it actually has some of our first reactions, our substitution reactions, and our elimination reactions we're going to work on. And then chapter 6 is all about chirality and basically the spatial orientation of certain groups. And so by splitting them a little bit like that, I think it makes it easier to understand the whole reaction concept as it goes forward. So that is my administration for the time. Anybody have any other questions?
Dr. David.
Yeah.
So this might be, it's not really a question. It's just like those videos that you've been posting, really, it's probably a pretty good strategy. Like, you know, coming up to the test on the 30th, like just watch those videos, go over your notes. And then like you were saying, like you post them after the lecture. So just always go over them and just kind of double check yourself. It's a good strategy, right?
Right. And I have the full videos, the full slides that I use in the videos are on Canvas, right? So you can see them there. The goals videos are on Top Hat. And actually the goals videos are the goals slides are on Top Hat. And so you can almost look at them as see it once, see it twice, see it again, and then do the homework. And it should start to, oh, that makes sense now.
Yes, okay. Sir. I appreciate that.
All right. So let me go ahead and share my screen for Chapter 7, Goal 1. Share screen. So I was describing it to another student in another class that, you know, organic chemistry seems like this horrible, you know, big bear. But if you take it in small bites, watch a little bit of the video, read the book, look at the goal, and then kind of get that concept in your head, and then look at the next segment. Because the videos online are kind of split up by kind of topics. You only have 1 or 2 topics in each of those videos. And then if you go back to the book and reread it and go, you know, then you can get a secondary look at it and then do the homework and try that and see if it works. So it's kind of that iterative process, maybe take 30 minutes at each chunk to try to learn each section of a video. That would be a good way to approach it, because then it's not just overwhelming, okay? All right, so chapter 7 is haloalkanes, okay? So up to now, other than talking about functional groups, we were talking about alkanes, which are hydrocarbons, and so it's only carbon and hydrogen. So now we're gonna add a new group to it, and we're gonna call this group a functional group, okay? So our goals for this is to, first of all, talk about the nomenclature of how we name these compounds right here and why they're called haloalkanes, et cetera. And then the second goal is to talk about reactions and leaving groups. So this halo group, this halogen that we have attached to our system, it has a polarized bond, and that polarized bond means we can use it to do chemistry. And so these are going to be our first reactions where we're using that halo group as a leaving group and not just adding something across a double bond. So this is going to be kind of a different way to look at things. Okay, and then the third thing, our third goal is we'll introduce a total of 4 different mechanisms. And so we've already added addition. That was in our previous chapter where we're adding stuff across, you know, water across a double bond or HCl across one. Now we're going to look at substitution reactions, which is the S's, and elimination reactions, which are the E's. Okay, and I'll describe each of those in detail and compare and contrast them so you can start to see how you can tell them apart and predict which one is going to happen. Okay, so haloalkane means that it is a carbon halogen bond. Okay, and so the general name is called haloalkane because it can be any of the halogens, you know, fluorine, you know, iodine, whatever, doesn't matter. Okay, now when we talk about haloalkanes, it's specifically a halogen bonded to an sp3 hybridized carbon. So there's 4 things bonded to that carbon, and one of them at least is a halogen. And the general rule for any hydrocarbon, that because those don't react very much, we can write it as an R as the general term, and then a dash, and then whatever functional group we have attached to it. In this case, we have a halogen, okay? And one of the key things about this halogen, if we draw our Lewis dot structure, is that it has 6 electrons as lone pairs. Okay, it had 7 electrons. If you look at it where it is on the periodic table, it had 7 electrons. It only needed 1 more to create its octet, and it did that when it created this sigma bond with carbon. Okay, so because halogens are always considered a substituent, they never change the parent name. Okay, so we always count them as a substituent, so that makes it fairly easy to name them because we don't have to worry about, oh, is it an oxo or whatever. No, it's always going to be the name associated with the halogen. So if it was fluorine, it turns the prefix to fluoro, chloro, bromo, and iodo. Notice they all have O's at the end. That signifies that they are substituents to those chains, okay? So just like all of our other rules, we locate the parent alkane. We name that parent alkane based on the number of carbons available to it. Then we number it by having our lowest number, okay? Then we indicate where the different halogens are. If we have multiple halogens, we put them in the alphabetical order, and we number them like we number other substituents. So let's go ahead and quickly run through these right here. So in this case here, we have a total of 6 carbons, but one of them acts as a substituent, so we have to call that the methyl group, okay? So if we numbered from this side, the first number would be 3, so we have to number from this side because our first number is going to be 2. And in doing that, we have our methyl group at 2 and our bromine on the 3 carbon. Now, just like all other substituents, we do it in alphabetical order. So we have 3 bromo, 2 methyl pentane for the 5 carbons in our pentane. Okay, and So that's how you name halogens. You just put them as a substituent and put them in alphabetical order. Okay. So in the case of this cyclohexene right here, remember when we name rings with double bonds in it, we have to name the first two carbons for the first two carbons which are in the double bond. And then you number it in whichever direction gives you the lowest substituent number. So in this case, it's clockwise, and therefore our lowest substituent is going to be on the 4 position, and it's only a bromine. So we call it 4-cyclohexene. Okay. Okay, there we go. Let's see. Okay, so over here, we also have this derivative when we have rings. We have a cis and tran in rings, and we do the exact same thing. Because the ring was named for the alcohol functionality, that's always at number 1, and then we number them from there on. In this particular case, we have the OH going behind the plane of the ring and the Cl coming out from the plane of the ring, which puts them on opposite sides of the ring, therefore we call it trans. Okay, so again, they're just a substituent, they never change the parent name. Okay, so there are some very common ones that we kind of need to think about the common names for these, because you will see them, like if you go to Home Depot and look at a paint stripper, you're actually going to see something called methylene chloride. Okay, now that's not the IUPAC name, that's the common name. So let's compare the IUPAC names to these common names we have. So if we have 2 chlorines right here on a methyl group here, then we call that dichloromethane. Okay, it would technically be 1,1-dichloromethane, but we only have 1 carbon, so it's pretty easy. But the common name for it is called methylene chloride. It's a really good solvent. It makes paint bubble up really fast. Okay. The next one we have here, we call trichloromethane because it has 3 chlorines on that methane. However, the common name for it is chloroform. And you may have seen in old spy movies where they put chloroform on a rag and put it over your face and you pass out immediately. It doesn't work that way. But it was originally used as an anesthetic, which is why they think that it works that way. It takes much, much longer. Then, if we go from that and move on to another one, by the way, if you have 4 chlorines on there, it's called carbon tetrachloride. So they actually follow the rule. On this case here, when we have 3 chlorines on one of the methyl group, but we've extended it by 1 more methyl group, it's called methyl chloroform. Think about it. This is the chloroform, and that's the methyl. And then this is used as a dry cleaning solvent right here. It's called tetrachloroethylene. Okay, and the correct name would be tetrachloroethene. It'd be 1122 tetrachloroethene, but the common name is tetrachloroethylene because it has the ethylene functionality and then 4 chlorines on it. Okay, so these are common names you're going to see. I might occasionally refer to them in class as chloroform. It's typically a solvent like methylene chloride and chloroform are very good solvents. Okay, the next set of common names we see for these halocarbons are what we call freons. Okay, and freons are used as refrigerants, and so when you compress them and release them, they absorb a lot of heat as they boil off, and that's why they're used in refrigeration units here. Now, they are ozone depleting, and so they actually have another set where they've added some hydrogens to it, and what that does is that makes them have a shorter lived life in the atmosphere, and they're not as bad. But the 2 that are of importance are the most common, Freon 11, which has 3 chlorines and 1 fluorine on a methyl group, and chlorine 12 right here, which has 2 chlorines and 2 fluorines. Okay, so if you think about it, Freon 11 has 1 carbon and 1 set of halogens, and Freon 2 has 2 carbons and a set of halogens. So that's one way to maybe remember it. But these are very common. You'll see this. Some of the newer ones have longer names like 113, and those are associated with the idea that also counting where the hydrogens are. So if you look at the two that are commonly used in air conditioners today, especially home air conditioners, they're called HFCs, or hydrofluorocarbons. So they have hydrogen on them, fluorine, and chlorine on them. And the designation number here tells you exactly where all the different substituents are, okay? In this case here, you don't have any chlorines, and in this case here, you have 2 chlorines and only 1 fluorine. Okay. But again, they're mostly gases at room temperature, and so when you compress them and release them, they absorb a massive amount of heat because of those heavy atoms in there. Okay, continuing on with nomenclature. Let's go ahead and do a few examples to make sure we have the idea here. So starting here, if we just look at this one right here, we have 1, 2, 3, 4 carbons, so that's going to be butane. And if we label it from left to right, that'll give us our smallest number. So we're going to get 2 chloro butane, yeah, butane. Okay. Notice there's no space or dash in between those. Chloro and butane just run together. All right, so let's look at this one right here. We still have a butane, but now we have a different isomer of it, so we can't name it for that. We have to go with the longest number. And so we can label it from either side, but we have a total chain of 3, which would make it propane. But labeling it from this side over gives us a 1 and a 2, which are shorter numbers. So what we're going to end up with is 1 bromo, 2 methyl, and then propane. Okay. So this one is going to give us a little bit more trouble. We have 1, 2, 3, 4, 5 carbons, so that we now have pentane. And we have to label it from left to right because that'll give us our lowest number, and that'll give us 2 bromo pentane. All right. Now the last one looks tricky, but it's really not. Okay. We have the ring has 6 carbons in it, so we're going to name it for the ring. Okay. This right here is one of those isomers that we were talking about. It's the T-butyl. So when we have tert dash butyl, okay, that's one group. We have bromine, that's the other group. Remember when we're alphabetizing with something with a name like iso or tert, it doesn't count for alphabetization, which means the butyl comes first. And then we have the cyclohexane. So let's string that all together. Because neither of these is the numbering from either side could be the lowest, we're going to name the alkyl group first. So it's going to be the 1 tert butyl, 4 bromo, cyclohexane.
Is there a dash between tert and butyl, or is that?
Yes, there is a dash between tert and butyl, and tert is usually italicized when you see it typed. Okay, I tried to italicize, but I can't write that.
Excuse me, can you explain real quick why bromo's on 4? Like, do you speak counting because of the tert butyls on 1?
Because when we have 2 substituents and they'll end up on the same thing, you put them in alphabetical order, and the lowest alphabetical order gets it first.
Okay, that makes sense.
So if you have it symmetrical, 1 on each side, you're going to number it from the side where the lowest alphabetical one gets the lowest number as well.
So, Professor.
Yes.
Did you start counting at the carbon 1, 2? That's 3 to the left of the bromide on the bottom.
Mm-hmm. Oh, okay. Well, no. So this would be position 1, position 2, position 3, okay. Position 4.
And that's just the route.
I'm sorry. What?
Oh, my bad. Is that like the route that you would usually always take? Is kind of go towards that bromide with a lower number?
Yeah, you would go both ways and figure out which way is lower number. It turns out that 1 and 4 is symmetrical on a cyclohexane, And so you can go either direction.
Okay.
Put a third substituent on there, it would change, but yes.
So,
Okay. So the naming, we're just using all our same rules, and it's always a substituent. Okay. So what we also have to think about is that there are different structural ways to do these halogens, and they have different reactivities. So we actually have special names for them. So for example, when we have, let me switch over to black here. When we have just CH3 with a chlorine on there, we call that a methyl halide, haloalkane. Okay. Now the reason we call that is that this will have different reactivity. We'll talk about that in the next goal, but we want to pay attention to how many carbons are attached to the carbon halogen on, because it gives rise to how easy that halogen can react. And if it can't react by one mechanism, it'll force it to react by different mechanisms. So when we have one other carbon attached to the carbon our halogen is on, which is over here, we call that a primary. When we have two other carbons, 1, 2, attached to the carbon with the halogen on it, we call that a secondary. And when we have 3 other carbons attached to it, we call that a tertiary. Okay, so and this is going to be knowing how many groups you have here is going to tell you everything about reactivity. So knowing that when you have a methyl group, it's just called the methyl, the primary, secondary, and tertiary. Okay. Okay. And the reason we label these things is because as we put things on that carbon next to the halogen, it makes it harder for things to react. Okay. So in the example of methyl, the methyl halide, or like methyl bromide right there, you have 3 hydrogens opposite the bromine. And that makes it really easy for something to come in and squeeze in between those hydrogens and kick off that bromine. Okay. However, once you put one methyl group on there, now our cone of attack has changed from the entire backside of it to being less of the this part of the carbon that can be attacked by something coming in and still displace that bromine. By the time you put 3 methyl groups on there, that means you have to hit right. It's like Star Wars trying to hit the bullseye to blow up the Death Star. It just gets really, really hard to do. So that makes it the methyls much more reactive. The primaries fairly reactive. Secondaries maybe, and the tertiaries are the least reactive to this kind of attack because they have such a small window that they can displace the bromine prop. And we'll start to see that when we look at the different mechanism paths in goal 2. Okay, so what we're going to see here is that this is the steric effect in the reactions we have. Okay, there's 2 things that control everything in our mechanisms here: electronics and sterics. Okay, in this case here, the sterics control the reaction. The more things you have around that, it makes it less likely for it to do that attack from the backside, and you have to use a different mechanism. Okay. All right, and we named all those already. Well, no, we didn't. We didn't name them. We named the first one. Oh no, we're identifying whether or not they're primary, secondary, or tertiary. So on the first one, on the top there, the chlorine derivative there, is it primary, secondary, or tertiary?
Is it tertiary?
And you can use the chat too. It is tertiary. You have 3. We have 3 carbons here attached to the carbon that the halogen's on. So this is a tertiary. What's the next one?
Primary.
Primary.
Yeah. So we'll see that we have a lot of different places where things can come in and attack on this side here. And the next one is
Secondary.
secondary. And what's the last one?
Primary.
Secondary.
Secondary. Yeah. I was hoping nobody would say tertiary. It's secondary because we're only looking at the carbons attached to the one where the halogen is. So it's secondary. Okay. So that's great. We can recognize our primary, secondary, and tertiary alkyl halides. All right, questions about nomenclature or the primary, secondary, tertiary identification of these haloalkanes? If not, I'm going to move on to our goal number 2. Okay. So our goal number 2 is talking about reactions that these things can do. And I kind of alluded to that. We're saying something has to come in and displace that halogen. And leaving groups. The halogen is our leaving group. And we need to talk about what that means. Okay. So in the case of reactions with haloalkanes right here, we have 2 different reactions that we're going to play with. One is called a nucleophilic substitution reaction, and the other one is called beta elimination. So this is going to be a substitution reaction with a nucleophile, and we call that the SN reaction. So it's substitution because we have a nucleophile. Remember what a nucleophile is. It's a Lewis base. It's looking for positive charge. It has electrons that it wants to make a new bond, okay? And it's nucleophilic, but instead of just adding to the carbon, it's actually going to displace something. So it's substituting something on there. So we have nucleophilic substitution. So imagine electrons or a negative charge is coming in to create a new bond and kicks out the halogen as that ion. The next thing we have is what we call beta elimination, and these are called E reactions here. And in elimination, what we have is that there'll be a hydrogen, 1 carbon over, and it can be in any direction there, as long as it's 1 carbon over, and the hydrogen's going to be removed. The carbon that the halogen is on is what we call the alpha carbon, because that's the one of interest, that's where the leaving group is. The one next to it's called the beta carbon. And so if you remove a hydrogen from that beta carbon and remove that halogen, that means you've created an acid. You've removed HCl. So this is the opposite of that reaction of adding HCl across a double bond. We're actually removing that HCl to create a double bond. And so these are called elimination reactions, beta elimination reactions. And we have 2 kinds of those that we're going to play with, okay? Now, in this example here, we have a nucleophile. Notice there's a negative charge on this oxygen here. Okay, so has a negative charge, it's looking for positive charge. So it can do 2 things. It can come in from the backside of this thing and substitute the bromine to create a new carbon-oxygen bond and break that carbon-halogen bond. Or it can come over here and react with this hydrogen and act as a base, eliminating that hydrogen, which then kicks the electrons that the hydrogen had in, and then that kicks the electrons out with the bromine, and we get the bromine charge here. Notice the same thing can do both reactions. So that's why we have to do our goal 3, compare and contrast SN1, SN2, E1, E2. Okay, so now let's figure out what all those things mean. Okay, so whenever we have an alkyl halide, we're looking at the halide as that functional group, the one that's going to change, okay? So it's common to have something that already has electrons on it come in and hit it such that it kicks these electrons out, and we have a new carbon something bond, okay? So we had a carbon halogen bond and we have a new something. The nucleophile can be a lot of different things. I'm going to show you that one in a minute. Okay, so in an SN2 reaction, okay, so we have our substitution reaction that's nucleophilic. And if we have our nucleophile come in and actually hit the molecule and kick out the thing, all in one step, we call that a bimolecular reaction. So there's 2 molecules have to be exactly in the same place to form that, and therefore we have 1-step reaction, okay? So the 2 counts for 2 molecules, okay? So in this case here, we had the molecules coming in. The first one was our hydroxide. This is our nucleophile, because it has our electrons on it, okay? And this is our second molecule. This is the methyl bromide. So we have nucleophile plus substrate are 2 molecules, so it's SN2 reaction, okay? And if we look at the energy diagram, we see that our starting materials start here. At some point, we have enough energy to have that hydroxide come in at the correct angle, because you have to come in opposite of where the leaving groups is going to leave. And then once it does that, once these bonds start forming and these start breaking, you cascade down into products. Okay, so SN2 reaction, bimolecular, one step, one hump on the energy diagram. Okay. Now, there's an alternate way to do this, and the alternate way to do this would be to have the halogen leave first. Remember, that was mechanism pattern 5, where you have a group leave to form an ion. In the case of an SN1 reaction, we have that group leave and we create that intermediate, okay? So we've created that carbocation. And then what has to happen next is the nucleophile has to come in and attack the carbocation. So because we had a unimolecular reaction, we had a molecule split itself apart without another molecule nearby, we have an SN1 reaction. So it's unimolecular. And because of that, because we formed this intermediate, that in this case is a carbocation, our reaction diagram has two humps. First breaking the bond, forming that carbocation, and then having that nucleophile come in and attack it to create that new bond, and then going down to products. Okay. So in this case, as in most two-step reactions, the first step is usually the slow step. And that's why it's usually what we call the rate determining step. So now, those were the two kinds of substitution reactions. So we're substituting the halogen for something else. The other thing we can do is eliminate a halogen and a hydrogen to create basically acid as a leaving group. And those are our elimination mechanisms. And just like with the SN1 and SN2, the numbers are determined by whether or not you have a unimolecular reaction or a bimolecular reaction. In the E1, you're doing the same thing. You are breaking the CX bond, the C halogen bond first to create your carbocation. And then the molecule can lose a hydrogen to lose that positive charge and generate your double bond. The other mechanism is that you have to actually have the base pulling on the hydrogen first, because that halogen can't leave all by itself. The base is pulling on that hydrogen, and as soon as it pulls hard enough, those electrons kick down, make your double bond, and then the electrons between the halogen and the carbon leave. Okay. So the 1 and 2 has to do with whether or not we form a carbocation. And so in the case of E1 and SN1, we form a carbocation. In the case of E2, SN2, we don't form a carbocation. They happen all at the same time. Okay, so let's look at this step by step. All right, so the first step in these SN1 or E1 reactions is to break that carbon-halogen bond. So when we break that carbon-halogen bond, the first thing that happens is we have these electrons that were here. That makes us have not an octet around our carbon. We have a formal charge of +1, and we have a stable ion. Note that bromine can act as a nucleophile because it has a negative charge and it has no. So, but in the case if you had something else that could act as a base, it would be stronger, then you could do it a different way. Okay, so the second step in our E1 reaction, because we're forming a carbocation, is something in solution is acting like a base, okay? So in this case, we just have methanol right here. It's not a very strong base, but you already have a carbocation. So what can happen is that the electrons from the oxygen can act as a base, start pulling this hydrogen away, and those electrons end up balancing our positive charge. Note we have an octet around carbon now. So we have a total of 4 bonds around carbon. It's happy and neutral now. And then we've generated our species here, which is protonated. And then we'll probably end up donating that protein to something else as well. All right. So this is our E1 mechanism because we form the carbocation. In an E2 mechanism, because it's bimolecular, the base has already come in and is pulling on the hydrogen first, okay? So our base is already tugging on our hydrogen right here to pull this hydrogen away. But as it's doing that, this bond is getting weaker and weaker. And then eventually it says, okay, you can have the hydrogen. I'm just going to use these electrons to kick into here. And when it does that, that now influences this polar bond to take those electrons away. Because remember, we can't have 5 bonds to carbon. We can only have 4 bonds to carbon. So this would be its 5th bond, and so it kicks it out as a leaving group. Why does it kick out the bromine as a leaving group? Because bromine leaves as the most stable negative ion, okay? So we're not going to leave with a carbon negative ion because those are very, that's not a very stable ion. We're going to leave with a halogen ion. Okay, so E2 reaction is bimolecular, happens all at the same time in one step. So make sure you know where those 1s and 2s come from in the E1, E2, SN1, SN2, because it seems backwards, but if you think about it the way I'm talking through it, you'll see. Okay, so now let's talk about nucleophiles and our substitution reaction and what they can form. Okay, so we can use anything that has a lone pair or a negative charge as a nucleophile. Okay, so what we can do when we do that, but each of them will form a different compound when we do. So let's look at this first one right here, hydroxide. Okay, so number 1, it has a negative charge, and oxygen can act, it can form a nice oxygen-carbon bond. So when we have hydroxide react with, in this case, we're just using a methyl halide here, it will form an alcohol. Now, you can also, just like water can be deprotonated, your alcohol can be deprotonated. When we do, we call that an alkoxide. This is an alcohol salt, and it's also a nucleophile because it has a negative charge. But when we attack an alkyl halide with it, we don't end up with an alcohol, we end up with an ether. Okay, so it's a carbon-oxygen-carbon bond to form that ether. Again, other electrophilic atoms we have are sulfur, and with or without a carbon. And so we can get a thiol, which is with the hydrogen on it, or a sulfide or a thioether with the hydrogen off it. We can even displace it with other halogens. Anything with a negative charge can displace those systems. So we can displace it with other halogens. So we can convert chlorine to iodine and bromine to iodine and convert them all back and forth just by controlling the reaction. Okay, now we have nucleophiles here, but they're not charged, okay? But the key here is they're nucleophiles because that lone pair can reach out and create a new sigma bond. So they are all Lewis bases, but they are all nucleophiles, okay? So when we do that displacement with ammonia, we end up with a alkyl ammonium ion. And the reason it ends up as the alkyl ammonium ion is we haven't lost the hydrogen from the nitrogen at this point. So we have 4 bonds to nitrogen, and therefore it's a salt, ammonium salt. We can even attack it with water, and when we do, we get a protonated alcohol, okay? So all we have to do is lose this proton, and that'll generate a neutral alcohol. And we can do it with alcohols too. It's going to give us a protonated ether. And when we transfer that proton off, it'll give us our neutral ether. Okay, so you're starting to see a theme about nucleophiles. Nucleophiles have a lone pair. A lot of the better nucleophiles have a negative charge. Okay, so what makes things better or worse nucleophiles? Okay, there's a couple different things. Okay, nucleophilicity. Okay, when we talk about nucleophilicity, it means the rate at which a nucleophile can attack. it's sort of kind of related to, you know, the more nucleophilic it is, the stronger a Lewis base it is, okay? And we typically know these because we measure these, okay? There's not really a theoretical reference to it. We're actually measuring these things, and we see them as they rack and stack in a different way. But there are some trends we can see, okay? So this table's in your book, and knowing, you can definitely look at some of the trends that we see here, okay? So in this first group we call good, okay? Right here we have large anions like bromine and iodine, and the sulfur anions are large anions, okay? And then we also have the oxygen anions. So what we can think about all of these is that they have that lone pair, and they are really willing to share those electrons in a very rapid manner, and therefore they are good nucleophiles. Okay. The next set we'll see are, number one, smaller anions. So they are a smaller charged species. Okay. And we have the acetate ions. Okay, so those are less nucleophilic, and if you think about that, the negative charge is being shifted from one oxygen to the other, back and forth, back and forth, back and forth. So that means that that negative charge is not always on oxygen. It's shared, and that takes it down its nucleophilicity. Then the next thing we have is the neutral sulfur compounds and the neutral amine compounds. And if we look on the periodic table, we have halogen, oxygen, nitrogen, and then right below nitrogen is sulfur. Right below oxygen is sulfur. And so that's why they're moving further and further away from being strongly electrophilic. Now, the last set we have are the neutral oxygen species. Okay, so we had charged oxygen species up here that were good. We had delocalized oxygen species, which were and now we have uncharged oxygen species, which are poor. Okay. All right, questions on that series. Okay, you can, kind of in your head rack and stack these, saying, oxygen, sulfur, and bromine iodine are most if they're charged. Then it steps down if they're more delocalized or not charged, and then the not charged oxygen species are the least. Okay. So now we need to talk about if the attacking species can be differentiated between good, medium, and poor. The leading groups can also be racked and stacked in that. And what we can think about it is that we have a nice trend. We talked about Lewis acids and bases, and we looked at these acids as a function of the stronger the acid, the weaker the base. Okay? So in this case, the weaker the base, the better the leading group. Okay? The weaker the base, the better the leading group. So let's think about that in terms of, so that makes HI, HBr, and HCl are the strong acids. Those are all have pKa's of less than 0, which makes them all very good leading groups. Okay, but iodine is more acidic than bromine, which is more acidic than chlorine. So iodine's the best leading group, bromine's the second best leading group, and chloride is the next. The next best leading group is water. Okay, and then because it's a neutral species, it makes it easy to leave. And we can easily get water as a leading group by taking an alcohol and protonating. Okay. So then a much, much less is actually having the acetate ion. Okay. So this is our first ion. Notice that was a middle nucleophile, but it's not a very good leading group because it is, when we lose it, it's a moderately strong acid. Okay. And then if we have the hydroxide here is next, followed by an alkoxide, followed by an anion. These three rarely leave as leading groups, okay? We occasionally see them leave in beta eliminations, but rarely do we see them leave. So what we're looking at is all of the halogens here are really good leaving groups, and that's why we introduced this concept of substitution in our alkyl halide chapter. Okay, let's see, we got, all right, plenty of time. Okay, so we have what's a good nucleophile, or what's going to attack well. Now we have what's a good leaving group, what can leave well. Okay, so I said on there, water is actually a decent leaving group, okay? But hydroxide is a poor leaving group. So we can trick that reaction with us by using acid to protonate a hydroxide before we even try to remove it. So in this example here, if we actually took water, sodium chloride, and this alcohol here, and just heated it up till boiling and boiled it all day, nothing would happen. Right here, we have water that could be a nucleophile. We have chloride, which is a good nucleophile. Nothing would happen. It just wouldn't leave because the OH is a poor leaving group and is a stronger base than the chloride. However, we can trick it by protonating the oxygen of the alcohol. We now create this protonated alcohol species here. Now, when the electrons break to liberate the protonated alcohol, we end up with a neutral molecule. We have a neutral molecule leaving. That's very stable, okay? So if that neutral molecule leaves, then we just have our nucleophile attack the carbocation that's left behind. So instead of running it in neutral water with sodium chloride, all we did was switch to water with HCl in it, and it protonates the alcohol and makes it leave as a leaving group, giving us our product right here. All right, quick test. What mechanism did we use to do this here? Is it an SN1 or an SN2 reaction?
It's SN1,
SN1 because
the carbocation.
we generated a carbocation. Perfect way to look at it. If you generate that carbocation, you're looking at an SN1 or an E1 reaction. Okay, so the strength of the nucleophile is important. How good the leaving group is important, but water is also important. Okay, so I'm sorry, the solvent is very important. Okay. If the solvent has something that can hydrogen bond, we call that a protic solvent because it can transfer a proton to something. It can basically acidify, an alcohol or something. Okay, so in the case of things that can transfer a proton, these solvents are going to favor that unimolecular reaction, favor that formation of carbocations. Okay, so if you start to see that you're running the reaction in alcohol and maybe a little acid, you're looking at the idea to form that carbocation first. So notice all of these things, water right here has a proton that it can hydrogen bond with. This is a carboxylic acid, an alcohol, and acetic acid right here. They all have acidic protons, okay? So they are all protic solvents. They can all hydrogen bond. Okay. In solvents that don't have a hydrogen that can be transferred, that don't have an acidic hydrogen, we call these aprotic, meaning non-protic solvents. So an aprotic solvent is one that will not hydrogen bond, will not transfer that hydrogen to a group. So that means that in that case, if we ran that same reaction with HCl in a non-protonated solvent, it would go through a different mechanism. Okay? It doesn't have the hydrogen to transfer, therefore it can't make a better leaving group. So whenever we have these aprotic solvents, solvents without hydrogens available to them, they form SN2 reactions. All right, and let's look at a couple solvents that are common. So we talked about this one today, dichloromethane, okay? So it has two hydrogens on there, but they're not acidic, and therefore it's not a protic solvent. Acetone, it's a really good solvent because that carbonyl makes it have a dipole moment and makes it polar. So it's a good solvent, but it still doesn't have any acidic hydrogen. This is the sulfur equivalent to it. It's called dimethyl sulfoxide. basically a sulfur version of acetone, and it's a really good solvent, just like acetone. And then we can also use these other like ethers and stuff like that. Notice there are no alcohols, no acids, no water in any of these. So that's the differentiation between aprotic solvents and protic solvents. And all your protic solvents wait around for that bimolecular reaction to happen. So we have three things now that can help us determine which mechanism we're going to be using. Okay, so that's goal 2. All right, now let's look at goal 3. Okay, so now we're going to look at each of those reactions specifically and then compare and contrast to see if we can identify strong nucleophile, good leaving group, poor nucleophile, poor leaving group, and solvent effect in each of these. All right, so SN1, substitution, nucleophilic, unimolecular, forms a carbocation. Substitution, nucleophilic, bimolecular, does not form a carbocation. Elimination, unimolecular, forms a carbocation. Does not, bimolecular does not form a carbocation. All right, so let's talk about just the SN1 reaction. Look at each step in that SN1 reaction. I'm sorry, SN2 reaction. The SN2 reaction, bimolecular, meaning it only has one step. Your nucleophile is coming in opposite where the leaving group is and starts to form a new bond with that carbon just as that bond between the carbon and the halogen is starting to break. Okay. That's where sterics are important. How many and how large the groups are right here will control that reaction. Okay. So in this case, both reagents are important because you have to have both reagents in that transition state at the exact same time. Therefore, the concentration of each of those needs to be high enough so that they have enough time to actually have enough energy to reach that transition state at the same time with the same enough energy to work. So they're going to come in, form this transition state right here, and then as soon as that bromine starts to leave, we now have our new product. Okay. But we have inverted the carbon center. Okay. What does that mean? That means because we had to form our new bond here, whatever was already attached to the carbon, if we're starting in this position here, it inverts. Imagine an umbrella in the wind. It starts like this, and then enough force on it is making it flip to the other side, okay? So if we had one configuration here, and we'll learn about RNS in the next chapter, if we had one configuration, it's actually gonna flip over to the other configuration. But the important part is to know we have this inversion right here. Notice we didn't form a carbocation, and therefore we were in a tetrahedral state. We went through a transition state, and we're in a tetrahedral state. Just to make sure you remember that. Okay. In contrast, with an SN1, we form that carbocation. And remember what the carbocation looks like? It's a trigonal planar, and it has an empty p orbital occupying that top and bottom, okay? So the first thing that happens is it's a good enough bond and forms a stable enough carbocation that it has the halogen leave first. Okay? This is most common in tertiary carbocations because those are most stable. It can happen in secondary carbocations. So in this case here, the first thing that happens is the bromide leaves. The second thing that now happens is we can even have a weak nucleophile attack it because we already have that positive charge. Okay. So, but the key thing here is we formed this flat trigonal planar and we have this empty p orbital. What does that mean about our final configuration? Okay. What it means about our final configuration is our nucleophile can come in on this side or on this side. So it could give us either configuration, the same configuration it had before, this shape here, or it could give us the opposite. and it's a 50-50 chance because it's a symmetrical bond. All right. So that being said, our unimolecular reaction, when we form those carbocations, is governed all about electronic properties, okay? So because tertiaries are much more stable than secondaries, which are much more stable than primaries and methyls, the tertiaries and secondaries react faster and are more common. In the tertiary halides and the secondary halides are more likely to do SN1 reactions than SN2 reactions because of the sterics, the electronics. In SN2 reactions, it's all about sterics. If you, the bigger a group you have on there, the more groups you have on there, the less likely it is to react because it has a smaller and smaller window of attack. And therefore, our relative rates are the opposite of SN1 reactions. The methyl and primary react the fastest, followed by the secondary, and the tertiaries react very, very slowly if they react at all, okay? So in our unimolecular, where we're forming our carbocation, electronics are the most important. In our SN2, where we have to have two molecules there at the same time, sterics is most important. Okay, so what does that mean? Okay, that means whenever you have a tertiary halide, you are probably always going to have an SN1 reaction. Okay, because of sterics, it's not going to happen. Whenever you have a methyl or a primary alkyl halide, you're always going to have an SN2 reaction because it's governed by the fact that there aren't big bulky things around and it can very easily attack from the opposite side of the halogen. The tricky one is the secondary, because the secondary can do both, okay? And so we can control that with looking at how good the nucleophile is and or the solvent. So tertiaries are always SN1, primaries and methyls are always SN2, secondary is the only one we have to worry about. Okay, so, and it has to do a lot with nucleophiles, okay? The stronger the nucleophile, the more likely it is to go SN2, do the bimolecular, because you have a good nucleophile and you have a slightly sterically hindered thing in a secondary. So with a really good nucleophile or a small nucleophile, you can make that SN2 reaction happen. If you have a poor or moderate nucleophile, it's going to wait around for the carbocation to form. Okay, so the nucleophile helps control which mechanism those secondary alkyl halides go. Okay.
Professor.
Yes.
So the good nucleophile, 100% with the SN1 and E1, and the moderate and poor are favored by the SN2 and E2.
No, the good ones. If we're talking about so the better the nucleophile, the more likely it is to do SN2.
Okay.
Okay, because it's good and it can come in and displace.
Yes, sir.
And the weaker they are, the more likely they are to wait for the carbocation. So the more these are going to go SN1.
That makes sense.
And if you have a secondary in particular, once if you have a good nucleophile, it'll suggest that it's going to go SN2 because you have a good nucleophile. But if it's a poor, it will definitely go SN1. So the secondary alkyl halide is the only one that can use both mechanisms, and it's controlled by how good the nucleophile is.
Okay, thank you for that. I was like, that cleared it up completely. Thank you.
Good, good. Okay, the other thing that controls it is leaving group, okay? The better the leaving group is, that makes it easier to get to a, it gets it easier to go to the carbocation. And if you have a good leaving group, you can have a less likely nucleophile come in and displace it. But it's all about the conjugate acid strength. So these are very strong acids, which make them very weak bases, which makes them great leaving groups. So that's also a factor as long, yeah. So I already did these slides. All right. So summary, methyl, you never see it form a carbocation, so it always goes SN2. Primary, you never see it form a carbocation, therefore it always goes SN2. And I'm going to skip secondary for just a second here. So these are always SN2. Tertiary, right here, almost always does SN1 because it's too bulky to do that. And it forms a great carbocation. Now, for SN2s, if you have a good nucleophile in an aprotic solvent, you can form that secondary carbocation. I'm sorry, that's not right. The secondary alkyl halide will undergo SN2 with a good nucleophile in an aprotic solvent. The secondary alkyl halide, if you put it in a protic solvent, is more likely to form the carbocation. And therefore, if you have a poor nucleophile in a protic solvent, you're going to get SN1. Okay. So what the real big takeaway here is that the primary and the methyl, you don't have to worry about the mechanism. It's SN2. Tertiary, you really don't have to worry about the mechanism. It's SN1. Secondary is the one you have to look at. And the the two controlling factors are solvent and strength of nucleophile. Okay. So just think of it, if it's a great nucleophile and there's no proton there to help some other leading group leave, then it's going to favor that bimolecular reaction. If it has a protic solvent and a poor nucleophile, it's going to wait, or that poor nucleophile is going to wait for it to make that carbocation, and that carbocation is easily formed in the protic solvent, and therefore those two factors are going to make it go SN1. Okay. Now, the last thing to remember here is we get inversion of configuration here because we're substituting, coming in on one side, going out on the other. Boom. We mixed because it can go equal, 50-50 on either side of that carbocation. It doesn't matter. Okay. So let's talk about the elimination reactions. Okay. So in the case of these, it's the same thing. We're looking at how stable is the carbocation. Okay. Since if we have an alkyl halide, we cannot form a stable carbocation. It's always going to undergo our E2 elimination, meaning our base is going to come in and, our base is going to come in and pull on that halogen first. We do not form a carbocation. So it's not this. In secondaries, just like before, solvent plays a role. If you do the reaction in weak and protic solvents, you get E1 reactions because you form a carbocation. Remember, these are the ones that form carbocations. If you do it in a strong base, then it can actually start to pull off the proton first and you get E2. However, tertiaries always form the carbocations. Well, in the weak, will form the carbocations, and with a good base, it has to be a really good base because of the sterics of this, it will react in the E2 mechanism. So the E2 mechanism is the one where it pulls on the hydrogen on the beta carbon first, and then the electrons cascade. So this forms a carbocation, this does not. This forms a carbocation, this does not. Okay. So let's think about whether or not something is going to substitute or eliminate. Okay. So we talked about nucleophiles, and some of the nucleophiles are just nucleophiles, but some of them are what we call bases, okay? And those are the nucleophiles that like to have a proton. So we might have a competition in things like hydroxide and alkoxide. All right, so, and because they can act both as a base and as a nucleophile, we actually have a competition between the two. We typically get a little bit of both, but we can tilt one toward the other based on our conditions. So in this case here, if we have a nucleophile, but it's also a strong base, like hydroxide or OH, we can do our substitution reaction and eliminate our halogen here. Or we can do that beta elimination and generate our alkene. Okay. So how can we tilt it one way or the other? One of the ways we can do that is by using our solvent control, a protic solvent versus a non-protic solvent. So for when we have secondary and tertiary haloalkanes in a protic solvent, we can actually get a mixture because the protic solvent promotes the formation of a carbocation. And so what's going to happen is that once you form that carbocation, depending on what else is in there, can it act as a base? Well, water is a weak base and methanol is a weak base. And therefore it can undergo those reactions, but they're not very strong bases, and therefore they undergo this substitution reaction. If we had a stronger base, like an OH here, we would undergo the elimination reaction. And actually, your halogens here can also act as bases sometimes. Okay. So let's look at whether or not something can undergo that bimolecular reaction. We have a nucleophile that can act as a base. Okay. So what we need to have in our system to have it eliminate is our hydrogen here has to be in a particular position. Our hydrogen has to be opposite or trans to our leaving group. If we can't get a configuration where our hydrogen is trans to our leaving group here, it will not undergo the E2 reaction. It will undergo the SN2 reaction. Okay. But if we can rotate our bond such that we can get this hydrogen, that means that we can pull this off, kick these electrons in, and kick out the leaving group. So it's all about whether or not you can manipulate. And this is controlled by sterics. How big these groups are will control whether or not you can do that elimination reaction. Okay. So the summary on this, and there are much more detailed descriptions in the videos online, by the way, is that the methyl will only go SN2 reaction. There are only SN2 reactions. There are no eliminations possible because there's only one carbon. We cannot form an alkene that way. Okay. So we only have SN2 and we cannot do SN1. Okay. With a primary alkyl halide, we primarily think it's going to do our substitution reaction as bimolecular or elimination as bimolecular. And when it does the substitution reaction, it's mainly because it is going to have a strong nucleophile that is in there and can do the substitution right here. Now note, these are strong bases too, but they are small and they act as nucleophiles. The only way to get a primary to undergo our E2 reaction is to use what we call big bulky bases right here. So these are things that aren't nucleophilic, but are bases. If it's a nucleophile, it's going to substitute. If it's a non-nucleophilic base, it won't substitute. So whenever you see T-butoxide, and that's what it looks like drawn out here, like that, think big bulky base, start thinking E2 mechanism. That's the classical base used in most E2 mechanisms. Now, move on to secondary and tertiaries. Okay. So secondary actually will do a good SN2 if it has a weak base but a good nucleophile. So things like the halogens or the acetates that don't act as bases very well will act as nucleophiles and will substitute. However, if they are a strong nucleophile and a good base, like hydroxide or the alkoxide, we're looking for the elimination products. Okay? Now, once you get down to the formation of using a protic solvent and weak nucleophiles, you have time for it to form the carbocation. And when you have the carbocation, you have a mixture of E1 and E2 products. So that's why the secondary is always the hardest one. You have to look at what the reagents are. Good nucleophiles that aren't bases, substitution. Good nucleophiles that are bases, E2. Poor nucleophiles, protic solvents, are going to give us our carbocations or our unimolecular mechanisms. With our tertiary alkyl halides, they can't undergo substitution reactions. There's just not enough space behind there. So we have a difference of SN1 and E1, and those happen when we have weak nucleophiles and weak bases because it waits around for the carbocation to form. Although we can do a good E2 reaction if we have a strong base. Okay, and that includes alkoxides and T-butoxide here. The tertiaries will undergo that E2 mechanism. Okay, and I think I have one more table here. Yeah, okay. So here's the takeaway. Okay, notice that with poor nucleophiles, nothing happens until we form a carbocation. So poor nucleophiles and protic solvents wait for the nucleophile. They wait to form the carbocation, so they just wait for it. If we have a weak base, so something that's not hydroxide or alkoxide, but it's still a good nucleophile, like iodine and the thiolate and the amines, we'll see substitution until we get to our tertiary. And then once we get to our tertiary, it has to wait around for the carbocation, and therefore we can get both SN1 or E1 products because we form the carbocation. If we have a strong base or an unhindered nucleophile, again, our primaries and our secondaries, our primaries and our methyls are going to do substitutions first. It's very difficult for them to do the elimination reactions because the formation of, well, this doesn't have a second carbon and this is more likely to form substitution because of sterics. But everything else is E2. Okay? And then if we go to a strong hindered base, T-butoxide, it's all E2 except for methyl, and occasionally you get some substitution right there. That's the only thing that can happen to make an ether. So when you have big bulky bases, you're forcing things to become E2 eliminated. I think that's what I'm saying. So, three things to keep in mind when you're trying to get this straight in your head. Solvent effect. Protonated solvents mean carbocations. Nucleophile effect. Good nucleophiles that can act as substitution reagents until you run out of space and you have to go to a carbocation. Strong bases like hydroxide and alkoxide will do elimination reactions unless they have very unhindered systems, so primaries and methyls. Strong hindered bases will almost always do E2 except with methyls because there's no other carbon on the methyl group. So it can't do the elimination. So the only reaction it has available to it is the substitution. All right, that is goal 3. Questions?
I have a quick question. Looking at this table, can you just explain what it means by unhindered and hindered nucleophiles? I'm just a little confused.
Okay, so unhindered and hindered, remember I said that Sterics were a major factor, especially in the alkyl halides. So these are what we call unhindered. Unhindered means that it's small and doesn't have a big bulky group attached to it. Okay, so if we let's compare these two alkoxides right here. So if we looked at hydroxide, okay, it's small. It doesn't have a big bulky group on it, right? If we look at methoxide, that looks really small, okay? Now let's move up to ethoxide right there. It's a little bit bigger, but again, it has all this space to act as the nucleophile because it has the whole all the lone pairs here. Now let's take isopropanol. Isopropyl alcohol, that if we make it the salt here, this becomes the first slightly hindered. See, this methyl group now is making it the area where the nucleophile can attack as a nucleophile here smaller. And then by adding that third group to get to this T-butyl group now, this is what we call hindered. So it's all about the groups that are attached to the carbon or that are next to that oxygen as the nucleophile. So hydrogen and methyl, really small. Straight chain alcohols, small. Once you start getting branched alcohols, that starts to hinder things. And by the time you get 3 branches on there, like the T-butyl alcohol here, that's what we call hindered. Okay. Does that explain hindered and non-hindered?
Okay, that makes a lot more sense. Thank you.
Okay. And typically we think of anything, all of the oxygen anions as bases. And we think of all of the nitrogen anions as strong bases. Okay. So, and that's again in the book and in the slides. All right, questions on that? We're right up on 150, which is about where we're supposed to end. So what I will do is I will go ahead and stop recording and you can stay behind and ask questions.